discuss about the parallel ladder circuit. Okay. So in order to understand parallel ladder circuit, you have to understand the concept of full ladder. Okay. So if you have gone through my last lecture where I discuss about the full ladder, you can easily understand when we have to use full ladder and how to use full ladder for a particular operation. Okay. Now, this parallel ladder, when we need to use that also you need to understand. Suppose what example I told in the previous lecture when I was discussing about full ladder, same example we can take. Suppose you have given two numbers. Okay, so one of the number is having 2 bit, the other number is also having 2 bit. Okay, so suppose the first number is this is I'm representing it by using A1, A0, and the number is 0, 1. And the second number is also the second number is B1, B0, and I'm using this representation. This B1 is actually representing MSB and B0 is representing LSB. And suppose the second number is also same, that is 0, 1. Now, if I have to add these two numbers, okay, so which circuit is there in digital electronics to add these two numbers? The answer is parallel ladder. So when each of the number is having more than one bit, in such case, we need to use parallel ladder. What I told, if you have to add two numbers where each of the number is having more than one bit, you have to use parallel ladder. So for this particular example, how we do the addition of these two numbers? So 1, 1 in binary addition, this 1, 1, 0, and you have a carry that you propagate to the next state. And this is 1, 0, 0, and the result is 1. Actually, this procedure we follow. Now, the same mechanism is used in parallel ladder. Now, if you can remember my previous lecture, I told if you have given this type of operation, so these two bits is very good that you can use a half adder to add these two numbers because each of the number is having single bit. However, if you see this left side part here, how many bits you need to add? You need to add three numbers and each of the number is having single bit. Okay, so in the left side part, three numbers are there. This is one of the number, this is the other number, this is the third number. Okay, and each of the number is having single bit. So in this case, half adder cannot be used to add these three numbers because you know in half adder you have only two inputs. Okay, so the possible solution is your full adder because in full adder you have three input. The two main inputs are A and B, and along with that one you can consider carry in also. So this is you can consider as carry in value. Okay, so the possible solution is full adder. So what does it mean? You have to use one full adder for this left side portion, and you can use one full adder for this right side portion. Now you can ask me because in the right side you have only two numbers. How this full adder can be used? So if I consider here carry is 0, carry input is 0, then it is very simple only. This is nothing but a simple full adder concept only you need to use for the right hand side. So you have A equal to 1, B equal to 1, and carry equal to 0 for this right side part. You have to add these two numbers. We will have two outputs. One sum output will be there and one carry output will be there that I am using carry out 1 to indicate this right side full adder. Suppose this full adder part 1. Now for this left side part also you need to use one full adder, that is full adder number 2. It will have two input. One input is this one input is this one, and the carry of the previous stage will be considered as another input, that is Cin. Okay, so for this particular example, how many full adders you need to use? Two full adders you need to use to do this operation. Okay, now the question is how to determine how many full adders you need to use. That is depending on how many bits are there in each of the number which are given for the addition. Okay, as for this particular problem, two numbers are given and each of the number is having two bits. So you need to use two full adder to implement this parallel adder. Okay. So what I said, how many full adders you need to use in the parallel adder? that is depending on how many bits are there in each of the individual number. Okay, if you have 2 bits, then you need to use 2 full adder to make the parallel adder. Okay. Now, how this circuit is given in case of full adder? I will discuss this one. So as I already told, for this particular example, if I take, you have to use 2 full adder. So this is the full adder number 1. What are the inputs are there? You know, in full adder, 2 inputs will be there. One is input number A0, this B0, because first of all, if these two numbers are given 0101 for the addition purpose, then you need to first add these two numbers, and each of the number is having single bit. So this is A0, this B0, where you can, for this particular problem, you can apply this one here in this input, and in this input you can apply 1 here, and for B0 you can apply 1, this one. Okay. And what about the third input, that is carry in? Because here no carry is there, so you can consider carry in equal to 0. Fine. So this full adder number 1. So in full adder, how many outputs will be there? 2 outputs will be there. One is sum, another one is carry. So carry in 1 I can write. C out 1 we can write. This is a carry out. Okay, this is carry out 1. Fine. The suffix 1 to indicate this carry out 1. Now, so same thing I need to do for this left side part also. So in this addition, in the right side part, if carry is generated, that you need to give it to the left side part. So for this particular problem, 1 is generated as a carry. So along with these two numbers, you need to add carry also. So for that purpose, for the this left side part, you need to use another full adder. So this is full adder number 2. So what you need to do here, you need to give the bit A1 and B1. So these are the inputs A1 and B1. Each of the input is having single bit. This, for this particular example, this is 0, and this B is nothing but, here also it is 0. Sorry. Okay. Now, and this carry, whatever it was generated from the previous state, that you need to propagate to the next state. So what does it mean here? Whatever carry you got in the previous full adder, that you need to give as an input to this full adder number 2. Okay, and from here you will get 2 output. One is sum and one is carry out 2. So CU2 can write. Okay, so what does it mean? If you do the addition of these two numbers, this 110, this is nothing but this S0, this is S0, and addition of this one, you'll get one carry here. So this carry has to be added with these two. So 1 plus 0 plus 0, this result is 1. So this one is your S1 here, and here the carry is 0. So this is coming in carry out 2. Now, if you want to represent the entire thing in a block diagram representation, then it should look like this one, where you have these inputs for this particular problem. You have these inputs B0, B1. You have the inputs of A0, A1, and one carry in is there. What we have considered here for this particular problem, this was 0. So in some other case, maybe it can be So other case also, this carry in should be 0. Is whatever example generally we take. So we need to consider carry in is 0 only. Now, in this block diagram representation, you will have two output for this particular problem, that is S0 and S1. This S0 and S1, and you have one common carry output, that is your carry out 2 for this particular problem. So whatever the final carry out you are getting, that is your this carry out. Means for this particular problem, carry out 2 is your this carry out. Okay. So as we have done the addition of two numbers and each of the number is having 2 bit, this is actually 2-bit parallel adder. Okay, 2-bit parallel adder. Now, likewise, if both the numbers are having 4-bit, then we have to use 4-bit parallel adder. And in that case, we have to use 4 full letters. So I think hopefully now it is clear to everyone. Thank you very much.